No one has ever witnessed this giant isopod consume a single bite of food, not by day, not by night, and in fact, not a single time in the last 1,782 days. Yet, this giant isopod remains alive, still mobile, arguably the only animal on Earth subsisting on 0 calories. These creatures simply will not die. While most deep-sea animals explode from pressure changes when brought to the surface, giant isopods hauled up from over 2,000 meters down survive just fine. Why are they so horrifyingly tough? Why evolve to endure the surface if they don't live there? And what can actually kill them? To see why they're so durable, we first need to know what they are. The answer? They're bugs. More or less. Flip a damp rock in your yard, and you'll likely find a little gray ball that curls up when touched a pill bug. This is a giant isopod. Genetically, they're practically the same animal. This one just happens to be 60,000 times heavier and lives at the ocean's abyssal plane. They share the same phylum, subphylum, class, and order, Isopoda. But that doesn't explain why the giant variant evolved to be so indestructible. Stop feeding a garden pill bug, and it will desiccate and die in about 2 months. Most humans last only weeks without food. Logically, this tracks. The larger you are, the more fuel you require. A blue whale needs millions of calories daily just to exist. A semi-truck needs more fuel than a moped. So, have giant isopods broken the laws of thermodynamics? Not exactly. An animal this large, this giant, should starve within months. But they inhabit the pitch-black, freezing void of the deep ocean, where food is incredibly scarce, not growing on trees. Compare that to the world of tiny pill bugs, where sustenance is relatively abundant. Evolution didn't pressure pill bugs to withstand years of famine because food was always around. Down in the deep, where meals are unpredictable, you need the ability to starve, or you're finished. Yet, saying evolution demanded this doesn't explain the how. This still seems to defy thermodynamics. Even existing burns thousands of calories for us. Giant isopods are ectotherms. Their body temperature is barely above freezing. They expend zero energy heating themselves. Their metabolism is so absurdly slow it borders on suspended animation. Their cells perform the bare minimum to qualify as alive. They also make remarkably few noticeable movements. Essentially, they are in a permanent state of ultra-relaxed bed rotting. But a slow metabolism is only half the solution. You still need some energy. This is where their second trick appears. When a food source finally descends, typically a massive dead whale carcass, the giant isopod doesn't eat until full. It eats until physically incapacitated. They've been observed gorging so intensely that their rigid exoskeleton restricts movement, their legs unable to lift their bellies off the sea floor. They become immobile, meat-filled boulders. They pack this feast into enormous lipid reserves in their liver biological battery packs, so energy-dense they can sip on them for years. It's the same concept as being overweight stranded on an island, but pushed to a bizarre extreme. This isn't mere theory. We saw it play out in real time with the most famous isopod ever. Number 1. That wasn't a grand nickname. It was simply the ID tag given to the first Bathynomus specimen at an aquarium, and it stuck. He resided at Japan's Toba Aquarium. In 2009, he feasted, demolishing an entire horse mackerel and filling those lipid reserves to the brim. Then, he simply stopped. For the next 5 years, keepers tried monthly to feed him, waving mackerel, dropping squid, practically begging. Each time, number 1 would sniff or poke the food, then walk away. He didn't eat a single bite for over 1,800 days, and then he died. The 2014 autopsy revealed something astonishing. He didn't die of starvation. His body wasn't empty. He seemingly died of old age. He had eaten so much in that one 2009 sitting that he was still running on the energy from a meal consumed during Obama's first presidential year. He could have gone longer. Factors like captivity, age, or stress likely ended him, but not lack of food. His very survival in that tank was itself a miracle. He was no longer in the deep sea but at surface pressure. For almost any other abyssal creature, such a rapid ascent is a death sentence. Bring up a blobfish, and it turns into a blob. Bring up a deep-sea rockfish, and its eyes bulge, while its stomach is pushed out of its mouth. It's gruesome. This is why giant squid kraken attacks don't happen. If you see one at the surface, it's dying, not attacking ships. This occurs because gases inside their bodies expand as pressure drops, like a shaken soda can exploding. The pressure provides structural support their bodies lack. Remove it, and it's like the animal loses its skeleton. So, how does the giant isopod survive a 2,000-meter ascent without turning to goo? Because it's built differently. Literally, unlike most fish, they lack swim bladders, those gas-filled sacs used for buoyancy. They are benthic roamers, designed to walk on the seabed, not float. No gas sacs means no expanding gas, hence no explosion. Furthermore, their exoskeleton is a masterclass in engineering. Composed of overlapping segmented plates, it allows them to curl into a ball, protecting their soft underside. This armor is built to withstand the weight of 2,500 meters of water. Because it's rigid and gas-free, it holds its shape perfectly at sea level too. A suit of armor equally effective in a submarine or in space. So, they don't starve, and they don't explode. But something can kill them. Ironically, while immune to oceanic pressure and starvation, they aren't immune to themselves. Giant isopods aren't intellectual powerhouses. Thinking costs energy. They're scavengers. When a large food source like an alligator carcass drops, they swarm it, piling on in a frenzy. With poor vision, they often mistake each other for food, biting whatever feels like meat. Fortunately, their thick armor usually results in a confused isopod rather than a dead one. They do have actual predators. Sharks will tear into anything on the seafloor, and in a frenzy, an isopod can be chomped through its shell. Octopuses are more strategic, prying at the shell to bite the soft inside with their beaks. But a major question remains: why get so big? Doesn't it attract predators? While they are a case of deep-sea gigantism, their reasons differ from creatures like giant squid. Yes, larger size makes them a bigger target for sharks, but predators are scarce at those depths. The benefits of mass outweigh the risks. Size lets them hold their ground on a carcass and tear off larger chunks. Crucially, a bigger body means more storage space for food. When a whale falls potentially your sole meal for 5 years, you need to stuff yourself maximally. Also, you need to reach it. These events are rare in a vast ocean. A dead whale 5 miles away would take weeks to reach on tiny legs, burning more calories than the food provides. Being giant allows for massive strides across the seabed for that one essential journey. Once there, you claim your share and retreat. It's peculiar because no other isopods approach this size. Terrestrial types are barely an inch. Antarctic isopods affected by polar gigantism reach only about 5 inches. Others, like members of Ceratocyrolus and Glyptonotus, max out around 3 inches. The rest are small to tiny. This makes the deep-sea Bathynomus line the only one to achieve truly giant sizes, nearly triple the next largest. Functionally, the isopod blueprint flattened body, simple gills, tough armor, shouldn't allow for large sizes. These traits impose natural limits. If giant isopods didn't exist, we'd assume the isopod form was meant for smallness. This very armor reveals a key weakness. Because they wear a rigid suit, they cannot grow continuously. The armor doesn't stretch, so they molt. For a giant isopod, this is a nightmare. Molting demands significant energy, something they avoid by bed rotting. When vulnerable with a soft new shell, they're easy prey, a soft shell crab special. Their genius strategy? They molt in halves. First, they shed the back half, wait for it to harden, then shed the front. At any point, 50% of their armor remains functional. It looks ridiculous, like wearing pants with no shirt, or vice versa, but it works. Yet, of all the threats they endure, one is absolutely fatal, the weakness that unravels their entire strategy: warm water. They can survive thousands of pounds of pressure, years of starvation, temperatures below 4 degrees Celsius, and even over an hour out of water. But a slightly lukewarm bath kills them almost instantly. Sudden warmth causes metabolic overload, spiking oxygen demand and misfiring enzymes. For all their incredible endurance, this is their kryptonite. They are among the most unique and adaptable creatures, but biology has its limits. It's rare to see an animal thrive so far outside its habitat, but something suggests, especially in number one's case, that he never wanted to leave in the first place.